going to have a look in this video at how we might be able to find the area under a curve. But the really important bit of this video is to do with looking at integration as summation, i.e. the idea that we can add up lots of little bits of something in order to arrive at a concrete block of something. Let's begin by having a look at something that's probably quite familiar. It's a problem that's often set GCSE and other levels of maths. Supposing we were asked, find the area of this shape. How might we do it? Well, one way that we would do it, perhaps, is to divide it up into a series of shapes, like that. That's one way. Each of these shapes is a standard area, a triangle, a square or a rectangle, whatever, and we can work out what its area is. Then we can get the area of the whole shape by adding together the area of each of these shapes. So from a shape that had no defined formula for its area, by breaking it up into more recognizable shapes, we were able to sort out what its area was. Okay, can we take that a little bit further? For a circle, there is a formula for the area A equals pi r squared. But if there was no formula, how might we proceed? One way might be to place a grid of squares over the circle, work out the area of each square and add them all together. However, some of the squares will not coincide completely with the circle. Thus, if we add together all the squares that contain any part of the circle, we will arrive at an overestimate of the area of the circle. We could try to attempt to correct this by ignoring all those squares that do not completely coincide with the circle. This would mean ignoring some of the area of the circle, and we would gain an underestimate of the area of the circle. However, we would now have two limits on the area of the circle, an upper one and a lower one. To trap the area of the circle ever tighter between an upper limit and a lower limit, we would need to make the squares in the grid smaller and smaller, so that the parts that were included or discarded were, in total, smaller and smaller. Now, what we're going to do is take that idea and use it to attempt to find the area underneath a curve. So, what we've got here is a curve, and what we're looking to find is, can we find the area underneath the curve? So, can we find in some way this area? And can we use the same sorts of ideas that we just spoke about with the circle? Well, let's take a very specific example. I'm going to have a look at the curve y equals x squared. I'm going to draw its graph between a and a squared. So this end point here is the point a squared. Now, how can we divide this up? Well, let's just put a limit to where we want to be. One way might be to say, okay, let's divide this in half. So we take a over 2, and let's take some rectangles. So there, and there. So there are two rectangles. This one here and this big one here. Now, at this point here on the curve, x is equal to a over 2. We're dealing with the curve y equals x squared, so that we know what this point is here. It's a over 2, a squared over 4. So we know the height of this rectangle. It's a squared over 4. So a guess, an approximation at this area underneath the curve, the area A, we know that A is in fact going to be less than the area of this rectangle, which is a over 2 times a squared over 4, plus the area of this rectangle, which is a over 2 times a squared, because that's the height of that rectangle. So we've got this area A. What we've got is an upper limit for it. We know it must be less than that. OK, if that's the case, then what about a lower limit? One way might be to take other rectangles, such as one down here of 0 height, and this rectangle here, where again this height is going to be a squared over 4. And we know very clearly that that means that this area A must be greater than 0. That's the area of this rectangle, plus a over 2 times a squared over 4. Now, what did we say about a circle to get a better approximation? We said we'd take smaller and smaller squares and put it on the circle. So in this case, what we want to do is take rectangles which are smaller and smaller in terms of their width. So let's draw this picture again, and this time let's divide these two segments into half again. So let's draw our curve again. We take a there, and so this will be a squared there for the curve y equals x squared. Now it's this area that we're trying to find, and we said that we would divide the base into half and then into half again and again there. Now a over 2 is halfway, but I want to keep this denominator of 4 if I can, so I'm not going to call that a over 2, I'm going to call it 2a over 4. And you'll see why I want to do that in a moment. Now, where are our rectangles? Well, there's a rectangle there. There's another one there. There's another one there. And a final one there. So here we've got 4 rectangles, all of which contain area that is underneath the curve, but all of which contain extra bits of area. So when we write down the areas of these rectangles and add them up, we will get an area that is greater than the area under the curve. So let's just write down the coordinates of these points, because the coordinates of these points will be the heights of the rectangles. So the y-coordinate there will give us the height of that rectangle. The y-coordinate there, the height of that rectangle, and so on. So this point here has an x-coordinate of x over 4, or a over 4 in this case. So that's a over 4. It will be a squared over 16. This one has an x-coordinate of 2a over 4. So it will have a y-coordinate of 2 squared a squared over 16. This one has an x-coordinate of 3a over 4, and so it will have a y-coordinate of 3 squared a squared over 16. And finally, this one will be, its x-coordinate is a, and so it will be a squared. And another way of writing that, to keep the pattern going, would be to call it 4a over 4. So it will be 16a squared over 16. Okay, let's write down the area of each of these rectangles. The width is a over 4. So we'll have a over 4 times its height, which is a squared over 16. Plus the area of this rectangle. Its width is again a over 4, because they're all of the same width, times its height, which this time is 2 squared a squared over 16. Plus, and now we want to move to this one. Its width is again a over 4. Its height is 3 squared a squared over 16. And then finally the end one, again its width is a over 4 times its height, which is, now I've written 16, but of course we know that 16 is 4 squared a squared over 16. And that is bigger than a. We know that is bigger than a. Let me just have a look at this. Can we see anything here that might be of interest to us? Well, first of all, we can see there's a common factor of a over 4. There's also a common factor of a 16th and a squared. So let's write that as a squared over 16. And what are we left with? 1 plus 2 squared plus 3 squared plus 4 squared is bigger than a. Now, what about our lower limit? Well, there'll be a rectangle here of 0 height. There'll be another rectangle here, another one here, and another one here. So we're looking at the area of that rectangle, the area of that one, and that one, where the upper boundaries of the rectangles are marked in red. What does that area come to? Well, we know that it will be less than the area under the curve, and it will be 0 plus a over 4 times by, now that's its height, the y value there, a squared over 16, plus a over 4, the width of that one, times its height, which is this one, 2 squared a squared over 16, plus the last one, where again we have a over 4 for the width, and for the height we have 3 squared a squared over 16. 3 squared a squared over 16. And so a is greater than, well, if we look what we've got, again we've got this common factor of a over 4. Again we've got this common factor of a squared over 16. Bracket, and 0 plus 1 plus 2 squared plus 3 squared. Okay, we could go on and do this again, but what we want is to try and do it in general if we can. So what I'm going to do is to take the same piece of area, the same piece of curve, the same piece of area, and I'm going to divide the x-axis into n equal parts. Here I had it divided into 4 equal parts. Now I'm going to divide it into n equal parts. And in doing that, I'm going to look at only a part of it. But the idea is going to be the same. And the same patterns that we picked out here, namely this sums of squares of the integers, is going to be there again for us to see. So, here's a section of the x-axis, a piece of the curve. We're interested in the rth strip. So let's just mark off a few of these strips. So there are a few of the strips. Now remember, each one is the same width. The total length of the x-axis we were looking at was A, and there are n strips. So the width of each of these strips is A over n. So each one has a width of A over n. Now that helps us count, because the rth strip, let's say it's this one here, must be r times A over n for its x-coordinate there, and here, for its x-coordinate, r minus 1 times A over n. Let's build up the rectangle on this strip. So there's the rectangle. Now what's the area of that rectangle? Well, the area of that rectangle equals, well, its width, which we know is A over n, times by its height, which is this y coordinate here. And remember, this is the curve y equals x squared, and so the coordinates of this point are r A over n, and then we must square it, r squared A squared over n squared. So the area is A over n times that height, r squared A squared over n squared. Okay. So this is the area of the strip, and it's bigger than this area underneath the curve. Let's call that delta A. Let's just tidy this up a little bit. We've got an A cubed, and we've got an n cubed, and we've got this thing r squared, and that is bigger than delta A. And what we want is the whole area. So we want all of these delta A's, and we want to add them all up. So we need to add up all of these, but that will still be bigger than the area as a whole. So let's add them all up. Sigma, that means sum, add up, A cubed over n cubed times by r squared, and we'll have from r equals 1 up to n. When we've added all those up, that will still be bigger than the area that we're after. Now let's look at the other rectangle, this one, the lower one. Now we can see that the height of this one depends upon this point here, and its coordinate is r minus 1 times A over n for x, and so its y coordinate is r minus 1 squared A squared over n squared. So what's the area of this smaller rectangle? Area equals Well, the width is still a over n, but the height is different. R minus 1 all squared, a squared over n squared, and this will be less than that area delta A. We now need to add all of these up to get an idea of the lower limit of the area. So let's do that. A will be greater than the sum of, and let's tidy this one up in the same way that we did that. We've got an a cubed formed by the a times by a squared. So that will give us the a cubed. And we've got an n times by n squared, which will give us n cubed. And then we've got this r minus 1 all squared, and we'll sum that from r equals 1 up to n. So now, let's write down these two inequalities together. So, we've got sigma r equals 1 to n of a cubed over n cubed times by r squared is greater than a is greater than the sum from r equals 1 to n of a cubed over n cubed times by r minus 1 all squared. Okay. This a cubed over n cubed is a common factor in each one, so we can take that out. Now, the question is, can we add up the sums of the squares of the integers? 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Remember, we had that before when we were looking at dividing it up into quarters. And I pointed out that we had 1 squared plus 2 squared plus 3 squared plus 4 squared, and that we'd see that again. And this is it here. We can see quite clearly 1 squared plus 2 squared plus 3 squared plus 4 squared, and so on. And the same over here. Can we add those up? Well, yes, there is a formula. There is a formula that tells us what the sum of the first n squares is. And the sum of the first n squares from r equals 1 to n is n plus 1, 2n plus 1, all over 6. Looks a bit complicated, but that's what it is, and in fact it's quite easy to work with. So let's put that in here instead of this one. So we get a cubed over n cubed times by n over times by n plus 1 times by 2n plus 1 all over 6 is bigger than a is bigger than. Now this is, if you like, r minus 1, so in a sense we're always one less than n, so we want n minus 1 times n times 2n minus 1, which is what we get when we replace n by 2n, all over 6 times by the a cubed over n cubed. Now, in each case, we've got this a cubed over n cubed times by 6. And in fact, we've got an n, look, here on either side that we can cancel. So we can cancel that and get a square, and cancel that and get a square. So I'm going to take the a cubed over 6 out, and I'm going to multiply out each of these brackets and put it all over n squared. So I'll have a cubed over 6 all over n squared greater than a cubed over 6 all over n squared. Now let's just go back and look at these brackets. This is n plus 1 times by 2n plus 1. So it will give us 2n squared, n and 2n, which will be 3n plus 1. So we'll have 2n squared plus 3n plus 1. And this bracket will give us again 2n squared, but then minus 2n and minus n will be minus 3n and plus 1. So again, 2n squared minus 3n plus 1. Now let's divide each term by n squared. A cubed over 6, 2 plus 3 over n plus 1 over n squared. That's dividing each term in turn by the n squared. Is greater than a cubed over 6, 2 minus 3 over n plus 1 over n squared. Now, it's taken us rather a long time to arrive at this position, but we're here where we want to be now. Let's imagine that we let n become very, very large. So the number of strips we're taking is infinite. They're infinitely thin, because n is very, very large. Now let's think what happens to a number like 3 over n when n is very, very large. Well, it goes to 0, and 1 over n squared goes to 0, as does 3 over n at this side and 1 over n squared at this side. So in fact, the area A is trapped between a cubed over 6 times by 2 and a cubed over 6 times by 2 again. So therefore, as n tends to infinity, in the limit, a is equal to a cubed over 6 times by 2, which is 1/3 of a cubed. It's trapped between these two bits that are the same here, because these bits disappear to 0. Now, we've done that for one particular curve to show that we can add up a lot of little bits to arrive at a finite answer, a lot of infinitely small bits to arrive at a finite answer. What we want to be able to do now is to do it in general to arrive at something that will work for all curves. So, let's see if we can extend what we've done to a more general curve. So here's our curve, let's say. And again, let's say that it runs from x equals 0 to x equals a. And what we're going to do is divide the x-axis up into very, very thin strips, each one of which is of width delta x. So we have x there, and the next mark on the x-axis is x plus delta x. Now, delta x is a small positive amount of x. So we've got our ordinates up to the curve, and we can complete a rectangle. So, what are the coordinates of that point? Well, this is the curve y equals f of x, and so the coordinates of this point are just x, y. That's the point P. what are the coordinates of this point? Well, the coordinates of this point, let's call it the point Q, are x plus delta x and y plus delta y, where delta y is that small increment there that we've added on as a result of the small increment that we made in x. Let's say that the area under the curve is delta A. So this is the area delta A. And the area delta A is contained between the areas of two rectangles. The larger rectangle, whose height is y plus delta y, and whose width is delta x, and so that's its area. And the smaller rectangle, let me just mark its top there, whose width is delta x, but whose height is just y. So its area will be y times by delta x. So if I want the whole of this area, I have to add up all of these little bits, which means I have to be able to add up all of these bits. So let's do that. A, the total area underneath this curve, is the sum of all these little bits of area from x equals 0 up to x equals a. And so therefore that area A is caught between the sum of all of these little bits from x equals 0 to x equals a at the bottom end, and at the top end the sum of all of these little bits from x equals 0 to x equals a of y plus delta y times by delta x. Okay, let me multiply out this bit. So we have sigma x equals 0 to a of y times by delta x plus delta y times by delta x greater than a greater than the sum from x equals 0 to a of y times by delta x. Now, we're going to let delta x tend to 0, just like we let n go off to infinity, which made the strips under y equals x squared come down to a over n, tend down to a 0 thickness. We're going to let delta x come down to 0. Now, what's going to happen when we do that? Well, certainly here we've got two very, very small terms. We've got delta x going to 0, so the change in y is going to be very, very small as well. So this term here is actually going to run off to 0. But when that happens, let's just cover that up, we see that a is trapped between two things which are identical. And so what we have is that a is equal to the limit as delta x tends to 0 of the sum from x equals 0 to a of y delta x. Now, we've actually made an awful lot of assumptions in what's gone on. And we've had to make them because at this level it's very difficult to do anything other than make these kinds of assumptions. Let's just have a look at two of them. For instance, one of the things that we have assumed is that this curve is increasing all the time for all values of x. But as we know, curves can decrease as x increases. Curves can wave up and down. They can go up and down as x increases. However, the results are still the same. We need to do it a little bit differently, but the results still come out the same. The other assumption that we're making is that, in fact, we can add up in this form lots of little bits and still get a definite, finite answer. And there's a whole raft of pure mathematics which assures us that these things do work. So, here we are at this stage. Now, this is very, very cumbersome language. And so, in fact, we choose to write this as a equals the integral from 0 to a of y dx. A is the integral from 0 to a of y with respect to x. And it's this notation which replaces that one. OK, supposing we actually want the area not from 0 to a, but between, let us say, two limits, a and b, two values of x and the curve. So we want, let's say, to find the area, let's have a curve here that goes between there and there. What would we want to do? Take that back to the y-axis there. What would we want to do? Well, this is the area that we're after. If we think about what that area is, it's the area from 0 to b minus the area from 0 to a. So this area that we're wanting is equal to the area from 0 to b, which is that, minus the area from 0 to a, which is that. Now, it seems quite natural to write that as the integral from a to b of y with respect to x. So we would evaluate whatever the result of this computation was at b and subtract from it the result of whatever the computation was at a. And so there we've seen how area can be represented as a summation, and that leads us to the traditional way of finding an area, which is to integrate the equation of the curve and substitute in limits. To conclude this video, we'll just look at one further result. This result will enable us to actually calculate areas by chopping them up into convenient segments. In just the same way as we began. If you remember that shape that looked rather like a dog, we're able to chop it up into convenient segments, find the area of the separate segments, add it all together. Well, this result is going to show us that we can do very much the same with a curve. So, let's suppose that for our curve we have three ordinates, x equals a, x equals b, and x equals c, and that they are in fact in order of size. A is less than b is less than c. Let's begin by asking ourselves, well, what's the area contained by the curve y equals f of x and these two ordinates and the x-axis? Well, it's from a to c, the integral of y dx. And we know that that is the integral from 0 to c of y dx minus the integral from 0 to a of y dx. Equals, well, let's introduce the ordinate b now by taking away that area. If I've taken it away, let's add it on in order to keep the equality the same. Now, if we look at this bit, the natural interpretation of that is again the integral from b to c of y dx, and the natural interpretation of this bit is the integral from a to b, y dx. So that what we've shown is that if we want to find the area from a to c, and there's some sort of inconvenience there around b, then we can work from b to c and from a to b and add the two together to give us the area contained by the curve.